let's now look at what happens for the other arm exponents. And maybe, since this is the other one where we have at least sort of given more or less complete proof of the fact that of the SLE computation, let's look at the two arm exponents. Right, so let's try to, so goal here, prove that the probability that in the discrete case, I have the origin here, I have a neighbor of the origin, that I have two paths of different color, one going from the neighbor of the origin to the boundary, and one going from the origin to the boundary, right? And this is of size n. And we want to check that this probability decays like 1 over n to the 1/4. So we want to prove that this is n to the minus 1/4 plus little o of 1 as n goes to infinity. Right, the same result as before, except that we now have two arms, one of each color, and n goes to infinity. And the exponent is not 5 over 48, but it's 1/4. So the first remark that we can do is, what is it? I mean, what did we exactly sort of prove given two arms in the SLE picture? So what we had that the following, which is, if I take an SLE process, started from 1, stopped at first hitting time of r, what we've seen is that the probability that it does not disconnect is of order, or up to constant, r to the 1/4, right, when r goes to 0. So what does this mean in terms of the discrete case? So this says that the discrete exploration process, so that means that the probability that the discrete exploration process started from here. So a discrete exploration process has to choose, which is the color to the right, which is the color to the left. So it starts from here, it goes to the inside here, and it hits this circle of radius r at some time. And so this converges to some function u of r when delta goes to 0. That's the convergence of this discrete exploration to the continuous one. And the fact that the disconnection times and so on converge also says that u of r is equivalent to r to the 1/4 as r goes to 0. Right? So what is this discrete statement? It's not exactly just that statement, I mean a two-arm statement like this, because it means this corresponds the event to the following event. We have a specified point, which is this guy. Right? And when you do this, you discover a blue arm here and an orange arm here, because when you go all the way to the end side, your right boundary is a blue arm, your left boundary is an orange arm. And conversely, if you have a blue arm here and an orange arm here, then the exploration process has to go between them, and it will hit the smaller circle before disconnecting. However, there's something that which is not entirely just the existence of two arms, because what we require is the order, right? So we have a starting point, and what we want is that if you go around, say, the unit circle in the clockwise way, in a sort of a trigonometric way, that you first hit the blue arm and then the orange arm. So this discrete exploration event that we're looking at is just, it's the probability that there exists two arms, blue and orange, when sort of that are oriented, sort of ordered clockwise, I don't know, anti-clockwise. When starting from 1, right? Or from 1 or for n, well, I mean from this point that you have. Okay? So let's call this event a hat. So if this is n, let's call this, let's associate these events where there's this clockwise ordering a hat, right? So here this would be, say, your, if this would be your delta R, and this would be your, 1 here and R, and the mesh size delta. So this would, event would be A of R delta with a hat saying that you have this ordering. And A would be the event that there exists just 2 crossings where you don't require, this ordering. So that means you are also happy if the blue one and the orange one are the other way around. So it's quite clear, of course, that the probability of A hat, will be smaller than the probability of A, which itself would be smaller than 2 times the probability of A hat. Because if A holds, then either you have this picture or you have the picture with the orange one before the blue one. But because of, flipping, the probability of having this picture is the same as the probability of having an orange one and a blue one here, because that's just, you just change all the colors. Everything is blue into orange, everything orange into blue. And so, clearly, the event that you are looking for, which is A, the probability that there exists 2 crossings, anyway, will be comparable to the event where you have 2 crossings that are ordered in a correct way. And so I voluntarily didn't say here this little r, large R, whatever. This is true, whatever definition of A you take, whether you take the arm starting from the origin, or starting from, or going all the way to or between 2 radii or whatever. It's just, if you prescribe the order given around one given point, then you just lose a factor of 2 at most. So that's one remark that you can make is that indeed the exploration thing tells you something about the 2-arm event, but it's not, you have to say a little something. And you start to see that, maybe if we take 4 arms, so just a little remark, if we take 4 arms of alternating color, instead of 2, the same thing will hold. That you have to have them clockwise. The question is which one you hit first. So blue, orange, or orange, blue. But this will anyway will have this flipping property. So this type of story will hold also. So the fact that we chose, arbitrarily the point where we started the exploration does not matter. Right? In the 1-arm, I mean, in the 548 case, it was clear that it doesn't matter because you were hitting anyway when you have a circuit of the wrong color, you had to go around wherever you started. Here, you don't discover exactly the same events, but their probabilities are comparable. Okay, so this tells you that basically everything we said for the upper bound will still hold. So the story about upper bound will hold, because you say, what is the probability, say, of 2 arms from 0 all the way to R0 to the n in the discrete case. So we're going to say that this is smaller than the product from j equals 0 to n minus 1 of the probability of 2 arms between R0 to the j and R0 to the j plus 1, right? Just because in each of the concentric annuli you will want to have 2 arms. And then you just say, well, in each of these guys, this is smaller than 2 times the probability that to have 2 arms, you know, clockwise or anti-clockwise with ordered from R0 to the J to R0. So, okay, I'm sloppy here, but it's on purpose. So roughly speaking, what I mean that in each of these annuli, what you want is that if I fix this point, then indeed I have the 2 arms with the order. So this is R0 to the J here, R0 to J plus 1. I have my 2 arms with the blue one here and the orange one here. And so this is exactly what is converging, right, to the quantity which we call U of R, which is equivalent to R to the 1/4. Right? So this guy here, and actually so this converges for each fixed thing when J goes to infinity, this quantity that is there to 2 times U of R0, right? And therefore, this is smaller than, if you choose R0 large enough, this will be smaller than R0 to the minus 1/4 plus epsilon, when epsilon is fixed, as before. You fix epsilon, then you choose R0 such that this holds, and therefore what you get here is that this is sort of that the limb sup of this guy. So it's exactly as before. So the limb sup of the probability of having 2 arms from 0 to R0 to the n to the power 1 over n will be smaller than just R0 to the minus 1/4 plus epsilon. Okay, then you conclude exactly in the same way as before. So for the upper bound, you don't have any problem. So you conclude that this probability this says that for any epsilon positive, for any rho, well, when rho is large, for all large enough rho, we'll have this is smaller than rho to the minus 1/4 plus 2 epsilon or something. So it's the same story as before, just decompose in annuli, have the upper bound in each of these annuli, and the fact that you are having something, you know, that you lose a factor of 2 at each time anyway is not a problem, because what you're using here is the fact that, you know, U of R0 was equivalent to R0 to the minus 1/4, and this is still the same, you know, since we're using this thing, it's still true for 2 times U. There's no problem. Okay, so for the upper bound, we are safe. Now we have to understand a little bit better what happens for the lower bound. So here we have 2 options. Basically, either, you know, you prove first all the separation lemmas, you know, in all generality, and then you use them here, easy version, and you reuse them later on when you want to get the theta of p. But I'm not sure all of you went to Pierre's lecture on separations. Well, maybe, okay. But let me try to sort of give you an intuitive picture. We want still, you know, to understand, to glue together what happens in the annulus. You know, we have 2 arms here, we have 2 arms here, and we want to, you know, glue them together to create 2 arms that go all the way. So FKG doesn't work. Right? So how do you do, you know, type of things using correlations if FKG doesn't work? Well, the only thing that you can do is just use, you know, the fact that percolation in different places is independent from each other, and use exploration ideas, right? Just say, well, just giving you one simple just a simple illustration. Right? Imagine that you have a rectangle like this. You start from here. And you look at the probability, say that there exists a picture like this. Right? So that there exists an orange guy from here all the way to the other part, a blue guy all the way from here to the other part, and that this blue guy is connected to the top and the orange guy is connected to the bottom. So how are you going to do this? Well, the way you're going to do is just start an exploration from here. If these two guys, you know, the blue crossing and the orange crossing exist, then you can go all the way to the other side. So you will hit the other side, and you will find the blue one and the orange one. Now, once you did this, you know the state of all the sides that are sort of between the blue guy here and the orange guy here that you have explored. So conditionally on this, all the sides here and all the sides here are not, you don't know what their status is. So conditionally on what you have already explored, you know that here, the law of what remains to be explored here is just ordinary percolation. So now you can say, okay, in this domain, I'm going to use Russo-Seymour-Welsh. In this domain, I have a probability at least 1/2 or whatever to have an orange crossing from here to here. And this probability is bounded from below. And independently, in this other domain, I can use Russo-Seymour-Welsh with the blue one. Right? So you just use independent things and independent events in the remaining domains, and that's all you do. Actually, if you think about it, if you think about the proof of Russo-Seymour-Welsh, that's the way it works. You know, it's just, you know, percolation. You just use the fact that things are independent. You start exploring things, and you just say, in what remains to be explored, you know, it's still ordinary percolation I can play with. So here you see that you have the probability that of this picture, you know, is larger than a given constant times the probability of having one crossing like this. And you don't use FKG, you use, you know, the fact that in independent, in disjoint things that are not yet explored by the exploration process, you can use Russo-Seymour-Welsh separately. So that's the idea. So what is the problem here about my two-arm story? So I want to say now that if I have two arms, say, in that big annulus, I will be likely, you know, and two arms from here all the way here, and two arms from all the way here, that probably I will be able to connect them together with positive probability. Now, there is a problem. There's a problem which is basically that suppose that your exploration process does something nasty just before the circle. So imagine that it does this. So here it comes very close to the circle. And then it goes all the way around and finishes here. So then you're okay, you still have found your two exploration guys, your two curves. But you know, now maybe if you have explored things, now the most likely thing, if this is very small here, it's very likely that because of Russo-Seymour-Welsh, you know, in the unexplored picture, you'll have a blue circuit here, and then you lose the, you know, then you have a blue loop, and you lose, right? You will not be able to have an orange path that the orange path will make it. So it's not the case like we had in the one-arm case where we said whatever way, you know, I have a one-arm picture in the large annulus and I have a one-arm in the small annulus, I have a positive conditional probability to glue them together in creating a one-arm that makes it all the way. That's not true because some configurations here are very bad. So in the sense that, imagine that I have sort of from the inside, you know, I arrive somewhere here. And, you know, and from the outside, I do this awful thing. And I end up somewhere here. So given this in the inside, given that in the outside, the conditional probability of creating two arms, that connect the two will be as small as you want, provided this guy here gets closer and closer. So what you want to prove is to have a lower bound for the probability of gluing together, two arms in one annulus and two arms in one other annulus, but when the two arms, are well separated. This is a configuration that you don't like. So the first thing to do is to say, well, the probability of having two arms in an annulus is comparable to the probability of having two arms in the annulus, but where the endpoints, are well separated, so that I will be able to use Russo-Seymour-Welsh and glue things together. So let me explain now the type of event you want to introduce. So let me take two annuli, say this is R1, this is R2. R2 is much larger than R1. And here, let's say this is 2 times R1, and this is R2 over 2. Now, the type of event that you want is the following, is that you're going to divide, for instance, this so we say, let's fix a small angle alpha. Fix a small angle alpha, and what you want is that there exists two crossings, so this one, say the red one, goes from here to here. The yellow one goes from here to here. And what you want is that these two guys have the following property, that if you start from here, they have an endpoint here, they have an endpoint here, endpoint here. That basically, if you take something with angle, so this is not a good choice here. You take a portion of the annulus, with angle alpha around the ending points here. Okay. So what you want is the following, is first of all, so I say it in words just so that you see the type of things we require. First of all, the red path here, so the intersection of the red path with the annulus between R2 over 2 and R2, so the intersection of the red path with a large annulus here, large thin annulus, that it remains in that little piece. Right? So, the red thing doesn't do this and come back here. No, it just, towards the end, you require the red part to go pretty straight here. Same for the yellow one. And same here and same here. Right? So in other words, what you want is that your other paths, your two crossings, they don't touch this, and they don't touch anything here. They are not allowed to penetrate there. And the other thing is that you're going to require is that these two landing things, these landing sort of areas, are themselves separated by an angle at least alpha. So here, that these guys are all these angles here that are between are of size at least alpha. Okay. Now, what you are going to end up with is the following. So imagine that this is what we call A hat of R1, R2, and this A hat depends on alpha. So this is much more difficult to realize. This is much more hard for a path to hold than just a two-arm exponents, of course, when alpha is very small. Or when alpha is fixed, If you require this to hold, then this is difficult. Right? Because maybe, you know, I mean, we don't know whether it's so difficult or not. The goal is to prove that it's not that difficult, yes?
Once you ask about, say, let us look at the red class.
Yes.
So you want that such class exists, and doesn't. So my question is, you ask that this class exists, and then it doesn't have a loop which may touch it, in principle, or it
May touch.
say out of the example which you draw.
Yes, I want this guy to hold.
Can you touch loop that touches?
Yes, yes. I'm just saying such a guy exists. I'm not saying anything else. Now, for each fixed alpha, right? The first claim is the following: is that what we can do is the following. Imagine that we know this holds in the large annulus. I mean, assume this holds between R1 and R2. Now, I can start an exploration somewhere here. And because of flipping, you know, either the red one will be to the right or the yellow one will be to the left, I will lose a factor of probability 2. This is not such a problem. So imagine that I start my exploration from here and that I have this picture. Anyway, you know, you are going to explore at most what is in here. Okay? Before you reach the center. So that means that starting from here, you will have explored, you will have a red boundary here, a yellow boundary here. Okay? And what you know is that in that piece between R1 and 2R1, right, the red guy, I mean that here basically you have, so the boundary here, everything on this side is red, everything here on this side is yellow, and that here basically you have, you know, some territory of angle alpha that you haven't explored yet, that is separating this yellow part. You know, maybe the yellow part is doing something like that or whatever. Because maybe, you know, maybe it's not that landing guy that you have explored. Maybe you have explored some other guy which was doing nasty things here. But anyway, there is the separating guy, alpha, on the other side that you haven't explored. There's a, you see? Here we had an alpha separating guy, and this one you will anyway not have hit. Okay. So you have this guy here. And here we know that on this part of the guy everything is yellow, and on this part of the guy everything is red. Okay? No, you don't have any yellow, you haven't explored any yellow stuff here floating around or any red stuff floating around here. Because you haven't penetrated it. You haven't penetrated this annulus. So imagine that you can do the same from the inside. So that means that in the inside, you know, I have explored here, I have R0, and that in the inside, I did the same up to R1 and R1 over 2, and that I have explored basically a red guy here, and I've started my exploration this time from the inside. Right? And I have reached the that boundary here. Okay, actually the guy you explore they will touch necessarily here anyway, because the first time you hit you get this. You have explored this, and again here somewhere you have a separation, you have a separating angle of alpha. So now the way you're going to use Russo-Seymour-Welsh is as follows, is that divide this guy of size alpha into two pieces of size alpha over 2. Okay. And now do the following. In that domain, right, create a yellow crossing. you haven't explored this part yet, so you just create a yellow crossing. The probability of having a yellow crossing like this is anyway smaller than the probability of having a yellow circuit in this annulus, in the entire annulus. And same for here. Here we take a red one from here. Sorry. Yes, that's right. Now here in the inner part, I do the same. Take a red one here and a yellow one here. So you see that conditionally on these good, the fact that these landing guys were nicely separated from the inside and from the outside, the probability of drawing this, conditional probability of drawing this picture is strictly positive. And here I'm just saying, conditionally on what I had before, I'm using Russo-Seymour-Welsh here, Russo-Seymour-Welsh here, Russo-Seymour-Welsh here, and Russo-Seymour-Welsh here, and everything, is happening in this disjoint event, so the fact that I'm using different colors is not a problem. So now, what we end up with is, given all this, that you have your two, I have these two annuli. This is, say, 2 times R1, and R1 over 2. And we found basically two little pieces where basically here you have explored everything. So here, again, okay, I should be careful. But, so the inside guy, you have explored something like that. And here somewhere else you have, say, a yellow guy here and a red-orange guy here. So here we see that we are going to, okay, I forgot something, so I will have to correct something slightly before. So here again, you have to be careful because we cannot, say now we have a positive probability to join together these two pieces. So what we'll have to do is basically say, well, the way we explored these yellow guys, the way we found this yellow crossing was from here, say for the outer annulus, was from the outside, right? In order to discover this yellow crossing, we took the first crossing we meet starting from the outside of the circle. So in that way, we explore these guys, and for the red guy, we explore these guys. But these guys are still, untouched. You haven't discovered them yet. And same for the inside, except that on the inside, we're going to explore the guys from the inside. So you're going to explore these guys, discover this crossing here from the inside, and discover this crossing from the inside. Okay? And so now we want to say that what we have is that we know the status of the cells here, we know the status of cells here, and here, and now we want to connect this one with this one, and this one with this one. And now we see, now we don't have enough space, we are trapped, right? So what we should have done here is to have another separating annulus. Right? Instead of having R1, 2R1, and so the picture, the correct picture should have been something like, say, R1 over 4, then R1 over 2 here. Here we have R1, and so that we still have, space. Of course, my factors of 2 are very, not very good here, so that we have the picture like this, so that still we have space here. And now again, you say, well, uniformly over once alpha is fixed, uniformly about where these guys actually are, I will be able, to find, say, to divide this picture into two pieces so that to have one tunnel here and one tunnel here. So that here I have a yellow crossing from here to here, and I have here a red crossing from here to here. And here I'm using, again, pieces I haven't explored yet. Okay? So you see the idea is to say that we are going to glue together arms, of different colors, but we have to be very careful, to explore things progressively and to be sure, that we are not, doing something deeply wrong in using knowledge, conditioning on some stuff and then resampling about what we had before. But this, is a good illustration of the fact that anyway, if you do percolation, everything is based just on this. You start exploring, some colors, using, exploration process or whatever, and then the rest is not yet touched, so you can still play with it and see that certain things hold or certain don't. And Russo-Seymour-Welsh itself, the proof is based on ideas like that. I mean, Menshikov in some way is also based on something like that. You are sort of conditioning progressively and next sausage, and then once this guy, the remaining stuff is still percolation and so on. So what this argument will tell you, right, is the following, is that something like that for each given alpha, and I guess this is quite clear, there exists a constant C which does not depend on R1, R2, and so on, such that for any R1, R2, R3, the probability of A hat of R1, R3 is larger than the constant times the probability of A hat. So, no, it's not hat. It was it was hat. Alpha. So the alpha, everything depends on alpha here. A hat alpha of R1, R2 over 2 times probability of A hat alpha R2, R3. Okay. So that you will be able, basically, if I have a good configuration between R2 and R3, I have a good configuration between R1 and R2 over 2, then with positive probability, I will be able to glue them together into a good configuration between R1 and R3. That's just the argument I told you. So start exploring from the boundary, you will discover, and then in the middle, you are able to glue things together using this progressive exploration idea. So now what remains, basically, to be understood is basically, is it true that this quantity is comparable to the A, right? Is it true that this is roughly of order A of R1, R3? Okay. So here there are two little remarks that you can make. Maybe I'll try to improvise an argument explaining you how I can proceed in this two-arm case, and then so what Pierre has explained to you in the separation lemma ideas was precisely a statement saying that you can find the alpha. You see alpha can be chosen. Right? So the thing, you can find an alpha small enough but fixed, such that basically this probability is always larger than a certain constant times this probability. Say that this probability, if alpha is large enough, is small enough, will be always larger than 1/2 times this probability. Okay. If you have this, then you are done because this anyway is larger than this, which is larger than this product, and then you have C1. Each of these guys is comparable to the probability when you remove the alpha and the hat, and then you have the same sub-additivity statement as in the one-arm case using Russo-Seymour-Welsh and FKG, and you are happy. Right? So either you prove by brute force, that using similar type arguments. Maybe you remember how Pierre did prove these, arm separation lemmas. But maybe I explain you now why it is true that these two things are comparable. There's one little remark that you can make here, and which I did on purpose. That you can make is that it would be enough, to have the fact that these two things are comparable if they were only well separated at the end or at the beginning. Here, in order to glue these things together, you just need that the outside guy that you glue together is well separated in the inside, and that the inside guy is well separated at the outside, because that's where you glue these things together. You don't need, that the things were nice here or were nice here. You just glue together here. So it would have been enough to prove that things are well separated to the only on the outside annulus near the inside annulus. Okay. let me give you one little argument that shows something that is enough in order to get these two arm exponents. It goes as follows. Suppose alpha is very small. And suppose you have a two-arm crossing, right? So you are looking at A2 over, at this crossing with two arms, but that you are not in the A hat case, right? So you're not in the case where things are nicely separated by little branches over there. So if you're not in the case where things can be nicely separated into branches in some way, so, okay, now I'm cheating. I'm just giving you, what I'm saying is slightly false, but just to give you the idea. If you're not in the case where things are nicely separated at the end, so imagine that this is imagine that we're looking at concentric circles like this, so 2 to the j, 2 to the n. Imagine that at 2 to the j, for this exploration process, when you start from here, you're not in a good situation near the landing points here. So if you're not in a good situation, that means, roughly speaking, that you're precisely in the bad picture, basically where you see something like that. And where this, basically, everything happens here in some small angle of alpha. So if you are in that picture, that because of Russo-Seymour-Welsh, again, with a high probability, you will find, if this is small, with a high probability, you will find sort of a red circuit that just after, a bit further than the radius of 2 to the n, will make that you are going to disconnect and that it's not possible to have two arms later on. Okay? So therefore, what you get is the probability of a bad crossing, that you're not in the good case, from 2 to the j to 2 to the n plus 1, 2 to the n. How can I say? Suppose let's put it this way. Suppose that the probability of well separating rated from 2 to the j to 2 to the n is smaller than some small eta, this is small, times the probability of just a crossing. 2 to the j to 2 to the n. Okay? So basically, suppose that you are not really sort of, that you don't have a nice lower bound on the ratio between this and that. Then what will happen is that necessarily sort of so either you are well separated and you have a probability eta to be able to continue nicely, say up to 2 to the n plus 1, to the sort of radius 2 to the n plus 1. And if you are not well separated, then you will have a very a very large probability of being disconnected immediately after that. So that means that if alpha was chosen small enough, then this will tell you that the probability that you have a crossing from 2 to the j to 2 to the n plus 1, that this will be smaller, much smaller than the probability to have a crossing from 2 to the j to 2 to the n. Why is that? Roughly speaking, because I look at the path, if I'm from here to here, anyway, I have to have two arms from 2 to the j to 2 to the n. Now, two things happened. Either they were well separated here, right? But this, anyway, happens only with conditional probability eta. Very small. Or they were not well separated here, but because I chose an alpha small enough, then if they were not well separated at level 2 to the n, they will, with a very high probability, die out immediately afterwards. They will not make it to 2 to the n plus 1. So what you get is that if you choose alpha small, but okay, you have to choose a slightly different definition, but if you choose alpha small here, what you get is that you can make this smaller than 2 eta like this. So in other words, the probability to get to distance 2 to the n plus 1 is much smaller than the distance to get to distance 2 to the n. Right? Now, there's one thing that you know a priori. This is the lower bound of the 2-arm exponents. A priori, you know that the probability to have something between 2 to the j and 2 to the n, there exists some positive beta such that this is larger than 1 over 2 to the j to 2 to the n to some power beta. This probability cannot decay faster than a power law, some given power law. Okay? So this you have a priori given. So now what this tells you is that if eta is too small, this cannot happen at too many n's. Right? Because if it would happen, say, if this would happen for too many n's, then this probability would decay, by a factor eta or 2 eta at each of these bad ends, and this will make it a power law decay for this guy, which would be faster than what you have here. Right? So that means that if you choose eta good enough, if you choose eta small enough, depending on beta, and alpha small enough, you know that this cannot hold for more than, say, 99% of the n's. Or the other way around, cannot hold for more than 1% of the n's. Because you know that, each time it happens, you lose a factor eta in your probability when you increase n. But you cannot, lose a factor eta too often, because anyway you have a lower bound for this guy. So if eta was chosen very, very small, you cannot lose a factor of eta more than, say, 1% of the time. Okay? So this tells you that basically you have a sort of a separation lemma, which is an average separation lemma, that tells you that there exists eta 0 and there exists alpha 0, such that for any R1, say something like for 99% of R2s, the probability of A hat of R1, R2 is larger than eta 0 probability of A of R1, R2. Just because of this a priori lower bound, you know that this cannot be, much smaller than this too often, because otherwise the power law will, the probability would decay too fast. And so this type of argument, is actually already enough to enable to get the lower bound for the lower bound you need. Basically, okay, maybe I shouldn't spend too much time with that, but okay, I don't know if I should tell you more now about this part or not. Let me just imagine that you want to find the lower bound for the probability of this product probability. So you want to find the lower bound between, say, what you have here and this R0 to the n. What you can do is, you can divide it into pieces, but the pieces in the middle, you don't necessarily have to choose them exactly, at the right place. You can choose them at the place where actually separation is nice. So suppose here things end up nicely separated here, and between the next guy here things are nicely separated here, and maybe here you lose a factor of 1/100 of the aspect ratio between R0 and the next one, right? Remember, this is R0 to the j, R0 to the j plus 1. Here I have some R0 to the j plus 2. Here. Suppose basically that in order to have this well-separated, to have the lemma on this well-separation here and here, maybe here you have to stop further because all the guys that get close here are bad. But anyway, this will be, this aspect ratio here will roughly be of order, R0 to the 1 over 100. And this 1 over 100 can be, taken so small, as small as you want, this a priori thing on the 100. And therefore here, once you are well separated, it will cost you something, to glue these together if the aspect ratio is large, but it will cost you something that you control and that can be taken very small if the 1 over 100 is getting very small here. So this was just a very hand-waving type of argument to indicate, to give you a hint into a direction that shows, that in fact, to get the well separation lemmas that you need here, you can just, cook up something with bare hands, which is not too bad, and always in the same spirit, saying, well, if they were, and if you look at what Pierre has told you, it's actually the same direction. We'll say, you cannot be not well separated at any level, because then, you have this will contradict the fact that some power law, you have a priori lower bound on power law decays of some given probabilities. Okay. So, but here you see that all this type of arguments are absolutely SLE independent, right? So it's not surprising that they were there before. Sort of, if you look at sort of that these type of arm separation lemmas and so on, they were in Kesten's paper before, and so he has this idea about protection walls and little fences and so on, which is exactly this idea that you can start exploring from one side, start exploring from the other side, and still in the remaining stuff put some Russo-Seymour-Welsh to glue things together. So, and that's really the argument. Okay. So in this two-arm configuration case, once you have the separation lemma, and you can get it in different ways. Of course, this lemma will hold actually more uniformly than just for 99% of the values of j's or n, but that will be enough. Then you can use convergence to SLE, and you will get exactly this type of things for enough R2s, which will enable you then later, to glue together these arm crossing events in each separate annuli, which are well separated, and then to get the lower bound using the fact that this is something you can approximate using SLE. Actually, there would be another way, to use directly SLE, right? Which would be a sort of intermediate way, which is more or less what I do in the well, I don't remember if I do exactly that in my lecture notes, which would be to say that if I take SLE, maybe that would be more convincing. I explore from the outer boundary here SLE, right? The fact that there exists two crossings. If you understand well Loewner's equation, you will see that when I do this guy, and starting say from when I reach sort of a radius 4r1, I condition my driving function w to be basically almost straight, to remain almost constant, not to oscillate a lot. If my driving function doesn't oscillate a lot, then probably, the SLE exploration process will go pretty straight. That's actually a true statement. So therefore, if you condition the driving function, to remain fairly straight, to remain fairly constant, starting from that point onwards, then between 2R1 and R1, what is going to happen is that this SLE, will go pretty straight here. And going pretty straight is actually a separation, a well separation property, because then once you've gone pretty straight, then you will be able to cook up, the gluing procedure. So you can also use, some property of SLE to say that the probability that they end up pretty straight is not too bad. But you have to be slightly careful. You have to say, well, first of all, here the probability here that things are nicely exposed is good, and then so you have to use some SLE property, and then the convergence of the discrete guy to the continuous guy tells you that you are still well separated, asymptotically, and therefore actually truly well separated. But again, you would have to, be very careful about what you do.
You're saying that for SLE6, if you want to have a sort of parameter in this case, then straight.
Yes, that the exploration guy is, remains in some cone or something guy, and that would be also enough.
Microscopically, it's actually very tortuous.
Right. Microscopically would be very tortuous, but basically, if it will still remain here, which is something. Of course, it's going to have positive probability, so a conditional probability. So it's likely basically to, and that's enough because then you're okay also. But of course, this is not quite enough for what comes next. So here, I guess so the message was the following for these other arm events. So this gives you the results for the theorem for the two arm events, the fact that the probability is, in the discrete case of two arms going all the way to distance, n decreases like 1 over n to the 1/4 plus little o of 1. And the similar argument works for four arms, except that four arms is even worse because, the separation stories, you have to be slightly more careful again. But the idea is really just, you have to define some nice crossing events of annuli, disjoint annuli, that are well separated. You have to do that. There's no way to bypass it. And these guys you will be able to do this type of exploration stories, to glue them together with positive conditional probability. And then you have to find a way to say that the probability of the well-separated guys is comparable to the probability of the guys themselves. And this is, again, you have to use in some way the argument that if they were not well separated at every level, then at some level you lose. And then things would decay too fast. So it's not possible. And then it's really just, cut and paste and be very careful about what you have explored so far, what you haven't explored so far, and so on. And, okay. So now what I want to explain in the, maybe, okay, now I'm sort of too careful with time. What should I start saying and what I should not start saying? So maybe it's better to conclude the percolation part. So in the similar way, so here, in the second part of this lecture, my goal was not, to present you a fully, self-contained proof of separation lemmas, because Pierre did that already, but sort of the spirit, that you have to glue things together, be careful, and in these two arms and four arms case, and that at least you have sort of the intuitive idea of how things go. And so in a similar way, you get basically, so the two arm exponents, that this will decay like n to the minus 1/4 plus little o of 1, and the probability of the four arm exponents this will decay like n to the minus 5/4 plus little o of 1. And here in that case, you have to separate the four landing things and so on. So this proves the results that deal with what happens at, for the arm exponent at the critical value, which were around in the physics literature. Now, the next step is basically how do you get to that theta of p, which is the probability that 0 is in an infinite cluster, grows like p to the minus 1/2 to the 5/36 plus little o of 1 as p tends to 1/2 plus. Remember, when you are in the supercritical case, When P is strictly larger than 1/2, then almost surely you have an infinite component, and this quantity theta of P measures in some way the mean density of this infinite component. The probability one given point is in that infinite component. And this will decay to 0 in a certain power law when P goes to 1/2. Now this Pierre has explained you in detail, I guess, also. This is this basically high scaling relations. So the scaling relation tells you that if you have this and the 5/48 result, then it implies this. And intuitively, maybe I just give you a 2-minute, intuitive explanation about where this 5/36 comes from. And of course, you have seen it already, but maybe it's worth just recalling you why it is so. So the idea is that you're going to coupling everything that happens at P equal 1/2 with what was happening just above P equal 1/2. So you start with the configuration at P equal 1/2. There's no infinite cluster, right? And then you increase slightly P, which means that, a fraction P minus 1/2 of the sites are flipped from closed to open. So a very small fraction of guys that were closed become open. And then you ask, did this little flipping procedure create an infinite cluster from 0? Right. So the picture, basically what you end up with is roughly the following, is that in order, here we let P tend to 1/2, right? So you are going to flip almost no site. You are going to flip almost nobody when P converges to 1/2. And then you ask the question, is that enough to go all the way to have an open cluster all the way to infinite? So the first remark, of course, is that if you want to have an infinite cluster just after having flipped a couple of guys, then already at P equal 1/2, you should already be in a very large cluster. So the situation at P equal 1/2 should be already very favorable, so that immediately afterwards you are at an infinite cluster. Of course, you imagine that, say, the cluster at the origin, is of size R1, which is small at P equal 1/2. Then the probability that you flip just, one of the boundary points of this clusters between 1/2 and 1/2 in factor P will be roughly, the cardinal, the size of the box R1 squared times P minus 1/2. Right? So it's quite clear that this is not a good strategy if you want to get P minus 1/2 to the 5/36 there, because here we already see that if the cluster at the origin is of size 5, the probability, that it's shortly afterwards at P, it is of infinite size, means that one of these 10 neighbors of this cluster of size 5 has been flipped, and this will only occur with probability 10 times P minus 1/2, so which is very small. So the picture is basically that at P equals 1/2, you already are in a cluster of some size, of some large size R. And how large will depend on P, actually. So you're already in a very good configuration at the cluster at the origin. The probability of being in that configuration will be roughly R to the minus 5/48, right? Because that's the probability that the cluster is already of size R at P equals 1/2. Now, what you want is that now you're going to flip. So this cluster of size R, you explore it from the inside. Right? So it has a boundary, outer boundary here. Right? So an outer boundary here of this guy is basically something telling you that here you have 3 arms. You have this guy going all the way to the boundary, and then you have the orange guy that wraps around it, the closed thing that wraps around it. Now, the question is, here, how many points? Now you're going to flip some points. you're going to between p equals 1/2 and p value p, you're going to flip some points from close to open. Right? So maybe you're going to make it through. Now, the entire scaling theory argument says that the important thing is to be able to puncture this hull, and to puncture it in such a way that at just one point, in such a way that on the other side you see, oh, here I already have a large cluster also. So by just flipping this one guy, that this will, propagate immediately to another very large cluster. Now, the point is that if I have two very large clusters that touch here, usually they will, have many contact points. So how many of these contact points do you have? Well, roughly speaking, a contact point here will correspond exactly to a 4-arm event, because that means that here I have a big cluster, here I have a big cluster, and they are separated by the hull of this guy. And I want a 4-arm event, of up to distance r, because my cluster had a size r. So how many guys here? If I have a cluster of size r, in average, how many guys do I have, on my boundary that, make it all the way, that are weak points such that I can puncture, and then by flipping just this guy, I make it all the way to there. Well, here in this box, you have r squared points, and each one will have a probability, so r to the -5/4 of being a weak point, because that's a 4-arm event of radius r around this guy. So this is the number of guys near the boundary that you have near your boundary points. Okay. So then you want to puncture them, right? And you want that by flipping between between 1/2 and p, at least one of these guys you are going to kill. So for this will, you see that this will sort of, if p -1/2 is smaller than 1 over this number, you will not hit any of them. And if p -1/2 is larger than 1 over this number, then you will hit one of these guys, if it's much larger or not. So the thing is that what you will want is that p -1/2, the things will, change where you have this. These points, if I'm all the way to distance r, I will have that many points. And if p -1/2 is much larger than this, then, one of these guys will be flipped. And if p -1/2 is much smaller, then none of these guys will be flipped with high probability. So what you want is roughly the critical value of r, right, such that if you already reach this distance, then when you flip from between 1/2, if you already reach this distance at probability 1/2, then with high probability, you will be able to to puncture all these hulls one after the other that you encounter. This critical probability, the threshold will happen when this happens. Right? So that means the following. You define r to be this number. So you define basically r such that r to the 3/4 is roughly p to the -1/2. Sorry, this number is very large, so it's 1 over this. The probability times the number has to be larger than 1 or smaller than 1. So you define r roughly in such a way. Right? So you choose it in such a way. And then you say, well, assume that I already have a cluster at p equal 1/2 all the way to some distance which is larger than this r to the 1 plus epsilon, say. Right? This will cost me a probability which is r to the -5/48, which then gives me p -1/2 to the 5/36, because you have the 3/4 that comes into play over there. So I assume that at p equal 1/2, I already have a very large cluster that reached that distance. Then between 1/2 and p, basically you are going to be able to go through all the hulls that are in front of you because you will have much more, much more weak points on these holes than the inverse of the probability of flipping each of them. So then you will make it all the way. And the contrary, if you don't reach, don't reach that distance, then you have this hole is there in front of you and will not be able to pierce to go through any of the weak points, and so you will not go anywhere by flipping between 1/2 and p. So that's the intuitive idea, right? And this tells you why, where this 5/36 come from intuitively out of 5/48 and 5/40. So again, this was a very hand-waving argument, just giving you, if you weren't at Pierre's lectures, or if you want sort of 5 minutes sort of intuitive description of this, this is how things go. Now here, you have to be careful because in order to make Kesten's arguments, scaling arguments work rigorously here, you have, roughly speaking, to use the separation lemmas uniformly near p equal 1/2. You need to do something like that. And in order to have the separation lemmas uniformly near p equal 1/2, there are certain things that, in the proof I told you with SLE or other type of things, there are certain ways to obtain the separation lemma that will not work. So you really have to put your hands into the sort of Russo-Seymour-Welsh and Kesten's technology, in order to understand what happens near p equal 1/2 also. So for those of you who will come on Wednesday, to these lectures in the afternoon, the entire question about what remains true near 1/2, in terms of SLE and what doesn't, and so on, will be sort of at the center of both Pierre and my lectures. Not at the center, but there will be sort of variations about this. Okay, so I guess sort of today you saw, I sort of had a glimpse of, you saw rigorously for the one-arm case, and you had, I guess, intuitive idea about how these things work for the other arm cases of these, how you go back from the SLE picture to the percolation picture. And you saw that you had really to be careful with Russo-Seymour-Welsh and so on, but on the other hand, you have a feeling that this is very standard, percolation techniques that you are going to use there. But it's really plain percolation stuff. It's not immediate, but it is not easy, but not so surprising either. And then you get the arm exponents, and then you get these other exponents that tell you what happens near the critical points using Kesten scaling arming that Pierre told you about last week, I guess, or the week before, maybe. So tomorrow, what I will try to explain to you is sort of give you some other models, so you will forget about percolation for a while and just see what the other SLEs are related to, conformally invariant models, what the Gaussian free field is, and loop soup measures and so on, sort of little stories that will be much more hand-waving, even more than today, about, what sort of, what people can prove, what were sort of recent results that have been proved in the last year or so, and where things are probably going and heading to. So I will probably say one little thing about 1/3 about Gaussian free field, 1/3 about loop measure, and 1/3 about what they call quantum gravity or random graphs. But that will be very hand-waving, just to give you an impressionistic idea. Okay, so I guess I'll stop here.